This is Perseverance, a one-ton robotic geologist roaming a crater that once held a Martian lake. Every rock it studies is a page from a world 3 billion years old. And when it finds one worth keeping, it drills. That drill cuts a perfect core, a cylinder of ancient Martian history sealed inside a titanium tube. It's not just a sample, it's a timestamp, a record of minerals, water, and chemistry frozen in place since before life even began on Earth. Inside its belly, tiny robotic arms handle each tube like fragile treasure, sliding, sealing, imaging, making sure no Earth contamination ever touches it. And once everything is perfect, Perseverance releases it onto the surface. Yes, it literally leaves the samples behind. Not by accident, but by design. Each tube becomes a breadcrumb in a planetary-scale treasure hunt. Perseverance has already built a depot, a carefully mapped grid of tubes lying in the dust, each one holding a different chapter of Mars's story. Clay from an ancient lakebed, igneous rock from deep underground, sand grains shaped by the wind, even trapped Martian atmosphere. Why so many? Because when these samples return to Earth, scientists will need multiple reference points, multiple chances to read the planet correctly. One rock might tell you about water, another about chemistry, another about time. And Perseverance isn't just collecting rocks, it's searching for patterns, the kinds of textures, organics, or isotopes that, on Earth, often whisper of life. Not proof, not yet, but hints. Every time the drill bites into stone, the rover gives us another chance to answer the biggest question we have about Mars. Could life have existed here? But samples lying in the dust won't tell us much on their own. To read them, we have to bring them home. So now the big question: how do we retrieve the samples Perseverance left scattered across Mars? NASA's plan is bold. First, a lander touches down near Perseverance, carrying a tiny rocket called the Mars Ascent Vehicle. It's the first rocket ever designed to launch from another planet. The rover drives over, hands off the tubes, and mission control begins one of the craziest robotic handoffs in space history. But if the rover can't reach the lander, 2 small helicopters, evolved from ingenuity, swoop out, grab the tubes, and bring them home. Once the tubes are loaded, the Mars Ascent Vehicle ignites. A plume of fire in a thin alien sky, and humanity's first payload rockets off Mars. The samples drift in orbit, waiting for the next step. ESA's Earth Return Orbiter. It hunts the sample container, lines up, and gently captures it like a cosmic catcher's mitt. Then comes the long trip home. So why go through all this? Why billions of dollars, decades of engineering, and a chain of missions more complex than anything we've attempted? Because inside those tubes are answers we cannot get from any rover. Earth laboratories can measure isotopes atom by atom, detect subtle organic molecules, look for microstructures that could hint at ancient life. Instruments no rover could ever carry. One sample might reveal how long water lasted on Mars. Another might show ancient chemistry drifting towards the edge of biology. Another could rewrite everything we think we know about how planets evolve. And here's the thing: even if we don't find life, we will still discover why Mars became a frozen desert instead of a blue world like Earth. Those tubes on the ground aren't debris. They're invitations, pieces of a story waiting for us to come pick them up. And when we finally hold them in a lab, we'll be holding the closest thing we've ever had to proof of whether we are alone or whether life has written its signature on more than one world.